Hello everyone, my name is Dr. Dipti Verma, Associate Professor, Computer Science and Engineering Department, Chhattisgarh Swami Vivekanand Technical University, Bhilai. Today, let's do a quick recap of the key concepts we covered in our previous lecture on Introduction to Deep Learning. Deep learning, a subset of machine learning, employs neural networks with multiple interconnected layers to discern intricate patterns from data, mimicking the human brain's complexity. A key application is image classification, which involves assigning labels to images, while image recognition encompasses broader tasks like object detection. Convolutional neural networks (CNN) excel in these tasks, utilizing specialized layers to capture visual features. Training involves data division into sets for learning and validation, with the model's effectiveness assessed on a test set. Transfer learning optimizes by reusing pre-trained models. Challenges include data quality, overfitting, and resource demands. Future prospects include explainable AI and innovative techniques like GANs and federated learning, shaping a transformative AI landscape. So, let's begin with the detailed understanding of the today's lecture on building a simple image classification model with TensorFlow. What is TensorFlow? TensorFlow is an open source machine learning framework developed by Google Brain that has emerged as a cornerstone in the field of artificial intelligence and machine learning. It provides a comprehensive platform for building, training, and deploying machine learning models, making it a crucial tool for both researchers and developers. With its versatile capabilities, TensorFlow supports a wide array of applications, ranging from image and speech recognition to natural language processing and recommendation systems. Its key features include flexibility, scalability across different hardware platforms such as CPUs, GPUs, and TPUs, and high level APIs like Keras that simplify model development. TensorFlow's core components, including tensors, computation graphs, and operations, facilitate the construction and execution of complex mathematical computations underlying neural networks. Its evolution over the years has introduced advancements like TensorFlow 2.x, which offers enhanced usability and immediate execution of operations. The TensorFlow ecosystem extends to specialized components like TensorFlow Lite for mobile devices, TensorFlow Extended for end-to-end pipelines, and TensorFlow.js for web-based applications. With its extensive community support, TensorFlow continues to drive innovation across various industries and remains a driving force behind the advancement of machine learning technologies. Dataset selection. Popular image datasets. When building an image classification model, selecting a right dataset is crucial for training and evaluating the model's performance. Here are two popular image datasets that are commonly used for image classification tasks. MNIST, that is Modeling National Institute of Standards and Technology dataset. What it is? It is a dataset consists of handwritten digits, each represented as a grayscale image of size 28 cross 28 pixels. It includes a training set of 60,000 examples and a test set of 10,000 examples. Application. It's often used as a beginner level dataset for introducing image classification concepts. It's suitable for testing and prototyping various neural network architectures due to its simplicity. CIFAR-10, that is Canadian Institute for Advanced Research Dataset. The dataset contains 60,000 32 cross 32 color image in 10 different classes with 6,000 images per class. The dataset is split into a training set of 50,000 images and a test set of 10,000 images. What are its applications? It is more challenging than MNIST due to its colored images and diverse object categories. It serves as an excellent benchmark for evaluating the performance of image classification models. Both MNIST and CIFAR-10 datasets are widely used in the machine learning community and serve as a starting point for experimenting with various image classification algorithms and neural network architectures. Researchers often use these datasets to develop and compare new techniques before moving on to more complex datasets and real-world applications. Importing TensorFlow. Importing TensorFlow is the first step towards utilizing its powerful capabilities for building and training machine learning models. In Python, you can import TensorFlow using the following code. Import TensorFlow as if once TensorFlow is imported, you are ready to start using its functionalities to create, train, and deploy machine learning models for a variety of tasks including image classification, natural language processing, and more. Loading image data using TensorFlow's data processing tool. When working with image data, TensorFlow provides convenient tools for loading and pre-processing the data before training a machine learning model. Here's an overview of how to load and pre-process image data using TensorFlow's data pre-processing tools. First, import important libraries. Import TensorFlow as if from TensorFlow.keras preprocessing.image import image data generator. Load image data. You can use the image data generator class to load images from directories and perform on the fly data augmentation. This is particularly useful for increasing the diversity of your training data and improving model generalization. Specify data directories, like when you have loaded TensorFlow.tf, train directory, then validation of directory, then create data generators with data augmentation, that is normalize pixel, rotate images, shift images. Then shift images vertically, apply shear, apply zoom, flip images horizontally, flip missing pixels using nearest neighbor. Next is normalize pixel, data generator and batching. The flow from directory method creates a data generator that loads images from the specified directory and pre-processes them according to the settings provided. It automatically batches the data, shuffles it, and applies data augmentation techniques during training. Data augmentation. This is optional. Data augmentation technique such as rotation, shifting, and flipping help increase the variability of training data, preventing the model from overfitting to specific patterns in the images. Use in model training. You can now use the train generator and validation operator in your model training process. When you call the fit function on your model, provide these generators as inputs. By following these steps, you can efficiently load and pre-process image data using TensorFlow's data pre-processing tools, enhancing the robustness and effectiveness of your image classification model. Data exploration. Visualize a few sample images from the dataset. Visualizing sample images from a data set provides valuable insights into the data and helps you understand its characteristics. Here's how you can visualize a few sample images using Python and popular visualization libraries like Matplotlib. Import Matplotlib, that is PyPlot, as import as from the TensorFlow.Keras pre-processing image import load img. Path to the directory containing sample images. List the image file names in the directory, then number of sample images to visualize, then create a subplot of num samples, rows and columns. Loop through and display the sample images. Load and display the image. Remove excess labels and ticks. Set the title of the subplot to the image file name. Then adjust spacing between subplots and lastly show the plot. Adjust the number of sample variables to specify the number of sample images you want to visualize. The code creates a vertical layout of subplots, each displaying a sample image with its file name as the title. This visualization will give you a glimpse of the data, helping you understand the content and quality of the image in your data set. Display class distribution. Displaying the class distribution of your data set is essential for understanding the balance and distribution of different classes. It helps you identify potential class imbalances which can impact the performance of your image classification model. Here's how you can visualize the class distribution using Python and Matplotlib. Import matplotlib.pyplot as plt. Path of the directory containing your dataset. Get the class names from subdirectories. Initialize a directory to store class counts. Count the number of images in each class. For create a bar plot of class distribution. Show the plot. Replace path to dataset directory with the actual path to your dataset directory. This code calculates and visualizes the number of images in each class using a bar plot. Each class is represented on the x-axis and the corresponding number of images is represented on the y-axis. The list directory function is used to retrieve the names of subdirectories within the dataset directory which represent different classes. The number of images in each class is determined by counting the files in each subdirectory. Adjust the figure size, labels, and title as needed to create a clear and informative visualization of your data set's class distribution. This information will help you make informed decisions about potential class imbalances and guide your pre-processing strategies. Design a simple model using TensorFlow's high-level API. Neural network from the foundation of modern machine learning, enabling computers to learn from data and make intelligent decisions. In the context of image classification, neural networks can be designed and trained to recognize patterns and features within images. Let's delve into the concept of neural networks and explore how to design a simple image classification model using TensorFlow's high-level APIs. Neural network. About neural network is a computational model inspired by the structure and function of the human brain's interconnected neurons. It consists of layers of interconnected nodes, that is neurons, that process and transform data. Neurons and activation functions. Neurons receive inputs, apply weights and biases and produce an output using an activation function. Activation functions introduce non-linearity to the model, enabling it to capture complex relationships. Layers in neural networks. Neural networks consist of layers including input, hidden and output layers. Hidden layers perform feature extraction and transformation. Introduction to high-level APIs. TensorFlow's high-level APIs such as Keras provide a user-friendly interface for building neural networks. Keras simplifies the process of creating, training, and evaluating models. Designing a simple model. Import the necessary libraries, that is, import TensorFlow as TF. From TensorFlow.keras, import layers models. Model architecture. Create a sequential model, that is, model equals to models.sequential. Adding convolutional layers. Add convolutional layers for feature extraction. Model.add layers.conv2d 3233 activation is equals to relu, that is input shape. Adding pooling layers. Add pooling layers to downsample and reduce spatial dimensions. Flattering and fully connected layers. Flatten the 2D feature maps to a 1D vector and add fully connected layers for classification. What is output layer? Add the output layer for classification. Model summary. Display the model architecture and parameters. Compilation. Compile the model by specifying loss, optimizer and matrices. Neural networks are composed of interconnected layers that process data. TensorFlow's high-level APIs like Keras simplify model design and training. We have designed a simple image classification model using convolutional and fully connected layers. The design model serves as the foundation for image classification. Further steps include loading data, training the model, evaluating its performance, and fine-tuning hyperparameters. Neural networks enable computers to learn intricate patterns, making them a powerful tool for image analysis and classification tasks. Model architecture. Architecture of the chosen model. Role of different layers. In this section, we will delve into the architecture of our chosen image classification model. We will examine the role and significance of different layers within the model, including convolutional, pooling, and fully connected layers. Model overview. Our chosen model is a convolutional neural network CNN. CNNs are highly effective for image classification due to their ability to learn hierarchical features. In convolutional layers, perform feature extraction by applying convolutional filters to the input image. They identify patterns such as edges, textures, and simple shapes. Pooling layers downsample feature maps, reducing spatial dimensions. They retain important information while reducing computational complexity. Flattering layer. Flattening converts the 2D feature maps into a 1D vector. It prepares the data for the fully connected layers. Fully connected layers process the flattened feature vector. They learn complex relationships and patterns from the extracted features. Output layer. The output layer produces the final predictions. It transforms the learned feature into class probabilities. Activation functions. Activation functions introduce non-linearity to the model. They enable the model to capture complex relationships in the data. Interpretation. Our model architecture enables it to automatically learn and identify relevant features from the input images. Convolutional layers detect basic patterns while subsequent layers extract high-level features. Fully connected layers are these features to make accurate class predictions. Understanding the architecture of our model is crucial for effective design and optimization. Each layer type plays a unique role in transforming raw image data into meaningful predictions. The power of CNN lies in their ability to automatically learn features, making them a cornerstone of image classification task. By comprehending the roles of various layers, we can appreciate how model processes and analyzes images, paving the way for successful image classification and recognition. Compiling the model, loss function, optimization algorithm, and evaluation matrix. Once the model architecture is defined, the next step is to compile the model by specifying essential components that govern its training and evaluation. These components include the loss function, optimization algorithm, and evaluation matrix. Let's explore each of these in detail. Loss function. The loss function measures the discrepancy between the predicted values and the actual target values. It quantifies how well the model is performing during training and guides the optimization process. For image classification tasks, a common loss function is categorical cross entropy, particularly when dealing with multiple classes. It calculates the cross entropy between the predicted class probabilities and the true one-hot encoded labels. Examples: loss function is equals to categorical cross entropy. Optimization algorithm. The optimization algorithm is responsible for updating the model's parameters, that is weight and biases, based on the calculated loss. The goal is to minimize the loss and improve the model's performance over iterations. One popular optimization algorithm is the Adam optimizer, which adapts the learning rate during training to efficiently converge towards the optimal solution. Here's the example. Compiling the model. Putting it all together. With the components defined, you can compile the model using the compile method. In this example, we have demonstrated the use of categorical cross entropy as a loss function, the Adam optimizer as the optimization algorithm, and accuracy as the evaluation metric. These choices ensure that the model is configured for effective training and evaluation on an image classification task. However, depending on the specific problem and dataset, you may consider using different loss functions, optimizers, and evaluation metrics to achieve optimal results. Training the model. Process of model training. Model training is the phase where the neural network learns to make accurate predictions by adjusting its weights and biases. Based on the provided training data, let's break down the process of model training and discuss key concepts such as batch size, epochs, and the training validation split. Data preparation. The data set is divided into training and validation sets. The training set is used to update the model's parameters, while the validation set helps monitor its performance and prevent overfitting. Batch size. Training is performed in batches where a batch is a subset of the training data. The batch size determines how many samples are processed in each iteration before updating the model's weight. A smaller batch size requires less memory but may result in slower convergence. A larger batch size can lead to faster convergence but may require more memory. Epochs. An epoch is a complete pass through the entire training dataset. During each epoch, the model goes through all the training samples and updates its weights. Multiple epochs are often needed to fine-tune the model's parameters and improve its performance. Training process. For each epoch, the training data is divided into batches. The model makes predictions for each batch, calculates the loss, and adjusts its weights to minimize the loss. After each epoch, the model's performance is evaluated on the validation set to monitor progress and detect potential overfitting. Training validation split. The data set is typically split into a training set and a validation set. The training set is used for model optimization, while the validation set helps estimate the model's generalization performance. A common split ratio is around 80% for training and 20% for validation. Building a simple image classification model with TensorFlow has equipped us with foundational knowledge, practical skills, and a sense of accomplishment. We have few more examples related to TensorFlow.tf which we will cover in our next lecture. Thank you.